GameSci.com. GameSci.com. Welcome to GameSci.com. I am Professor Chris Ferguson.
Hello and welcome to the lesson on recursion. I'm Professor Chris Ferguson. Dictionary.com tells us recursion is the process of defining a function or calculating a number by the repeated application of an algorithm. My definition, however, is quite a bit more simple. It's a method that calls itself, and that's all recursion is, when a method calls itself. You can see over here I have a method doCollide, and right in the middle of doCollide I call doCollide, and whoop, it turns around and executes doCollide again. That's all recursion is when a method calls itself. So let's talk about recursion, a method that calls itself. Collision detection is vital to programming video games, but we need to start with understanding recursion. Here we have a simple call to a method named doCollide, passing it the parameter argument of 4. The only thing new here is doCollide is a recursive method, which means it will call itself. Let's trace the execution of the code and see what happens. The argument 4 is assigned to the parameter sector, a local variable. Remember, parameters are local variables at the start of the method. You can see I've drawn the variable here, and that 4 from the argument is assigned to the parameter sector. So on this first line of code, 4 greater than 1 is a very true statement. As a true statement, it's going to execute the code in the if block and call doCollide. That is the recursive call. In the middle of doCollide, the method doCollide is called. Whoop. The argument passed to the parameter sector is 4 minus 1. Sector contained a 4, so 4 minus 1 is a 3, so we're sending a 3 off on the second, or the recursive call, to doCollide. The argument 3 is then assigned to the parameter sector, again a local variable, at the start of the method. Here's the new value of sector. It comes from this 4 minus 1 that executed before the call. 3 greater than 1 is definitely a true statement, so it's going to go in and execute the code in the if block again. Whoop! Here's our recursive call. This time 3 minus 1 is a 2, so a 2 will be passed as a parameter to doCollide. So in the middle of doCollide, we call doCollide again. The argument this time was sector 3 minus 1, or the value of 2, as the new input parameter. So here's our 2. Our 2 came from the 3 minus 1 that happened here. The argument 2 is assigned to the parameter sector. Again, this is a local variable. Parameters are local variables at the start of a method. Now, with a 2 in that variable, 2 greater than 1 is still a true statement, so it's going to execute the if code. And when it executes the if code, it's going to do the recursion again. Whoop! This time, however, in the middle of our doCollide, we call doCollide, the argument passed to the parameter sector is going to be 2 minus 1, or 1. The value passed to doCollide is a 1 this time. That's going to be very important shortly. The argument 1 is passed or assigned to the parameter sector number, which is a local variable at the start of the method. We now have a 1 in sector. And when we evaluate the if statement this time, 1 greater than 1 is definitely a false statement. This stops the recursion. It's very, very important. A method can't call itself forever. We have to have a condition that stops the recursion. And when sector gets to 1, it will definitely stop. This if statement is false, so it will skip the if block and go to the next statement after the if, which is the end of doCollide. So we're going to exit doCollide now with the call for sector equal to 1. Now, we had previous calls to doCollide. Remember, we called doCollide with a parameter of 2. Well, we still have to exit doCollide. After this line of code executes, when the parameter was 2, we still have to execute that code. Then we have to execute when sector number was 3. Remember the call to do collide when we did a 4 minus 1? Well, we still have to exit that call to do collide. And finally, we're back to the original call of do collide. We called do collide 4. We have to return from that execution. And this time, we're going to return for real. This is the return statement that will take us back up to here. We return to here just after the call to do collide, and this recursion is now done. So there you have it. That's a simple example of a recursive method. Fairly simple and straightforward. Let's move on to a more detailed version. Let's look at recursion and the stack. According to dictionary.com, the stack is a data structure for storing items which are to be accessed in a last in, first out order, or LIFO, last in, first out, meaning the last item we place into it is the first item that comes up. Now we're still going to do recursion here, and you can see here the method Quadrant 4 is going to call the method Quadrant 4, so whoop, we'll turn around and re-execute Quadrant 4 right in the middle. So definitely recursion, but this time we're going to see how it interacts with the stack. So recursion in the stack. How does recursion track how many calls are made? The answer is called the stack. Every time a method is called, the return address and values of local/parameter variables are pushed onto the stack. And when they return, they're popped off the stack. So every time I make a method call or a method return, something's going to happen to the stack. So let's call a method named Quadrant 4, passing in the argument our value of 0. So this is my original call to Quadrant 4, and I'm going to pass it as 0 as the argument. The call to Quadrant 4 is pushed onto the stack with the value 0 for the parameter quad. So this 0 here is assigned to the variable quad over here. Now look what happened to the stack. We pushed onto the fact that Quadrant 4 was called, and it was called with a value of 0 for a quad. Into the code we go. 0 greater than 3 is definitely a true statement, so it's going to be executing the code in the if block. And it looks like some recursion is going to happen. Bang! There's our recursion. Quadrant 4 is called in the middle of Quadrant 4. The argument passed to the parameter quad is going to be 0 plus 1. Our original parameter was 0. We add a 1 to it, and the new argument on the second call to Quadrant 4 is going to be a parameter or argument of 1. So as we execute Quadrant 4 a second time, you can see we pushed onto the stack. The argument 1 is assigned to the parameter quad at the start of the method. The call to the parameter, the fact that we called Quadrant 4, was pushed onto the stack. And the new parameter, quad equals 1, was pushed onto the stack. Two things got pushed onto here. Quadrant 4 was executed, and quad equals 1 was the value of the parameter. That's what the stack does. It keeps track of the calls and the values of the variables inside the method. 1 is still less than 3. That is very much a true statement over here. So if it's a true statement, we're going to execute the code in the if block, and whoop, there's our recursion again. We're going to call Quadrant 4. That is a recursive call. In the middle of Quadrant 4, the method Quadrant 4 is called. The argument passed to the parameter quad is 1 plus 1 or 2. The current contents of quad is 1. You add 1 to it, and the new parameter value is going to be 2. So we come into the method again, Quadrant 4, with a quad equal to 2. Argument 2 is assigned to the parameter quad at the start of the method. You again see the call to Quadrant 4 is pushed onto the stack, and the value of the parameter this time, which is 2, is pushed onto the stack. This is telling us that there are 3 executions of Quadrant 4 outstanding at this point. 2 less than 3 is very much a true statement. As a true statement, we are going to execute the if code. Whoop, there's our recursion again. In the middle of quadrant 4, we're going to call quadrant 4. The argument passed this time is going to be 2 plus 1, or the value 3. 3 is going to be the new value of quadrant when we execute quadrant 4 again. So we come again. The argument 3 is assigned to the parameter quad, which is a local variable at the start of the method. You can see on the stack here, quadrant 4 has been placed on the stack again with the value of quad being 3. Every time quadrant 4 is called, it's kept track of on the stack. But this time it's different. Quad less than 3, 3 less than 3 is very, very much a false statement. As a false statement, this is going to stop the recursion. It's extremely important that recursion stops. Recursion cannot keep calling itself over and over, or it would fill up the stack. So recursion has to have a terminating condition, something that stops the recursion. And when quad gets to 3, we're going to stop. You can see because the if statement is false, we're going to hit the closing curly brace of quadrant 4 and exit the method quadrant 4. Now, here's the exit of quadrant 4. Remember, this was for when quad was equal 3. We popped that call off the stack. It's no longer running. Quadrant equal 3 is now done. We're going to pop it off the stack. Do take a note, the top of the stack now has quad equal to 2. Because we've got to go back and finish the execution of quadrant 4 when quad was equal to 2. So now we're finishing up the call to quadrant where the parameter was 2. We popped that call off the stack. It's gone. And we finished the call of quadrant 4 with the parameter of 2. Note what's at the top of the stack. The next execution of quadrant 4 is going to have a value of quad equal to 1. Or finish that call to quadrant 4 where quad was equal to 1. We pop the call off the stack. Look at the quad equals 0. The quad equals 0 is the last one. So we're going to exit quadrant 4 when quad was equal to 0. Now here's interesting. After the pop, there's nothing left. There are no more calls to quadrant 4 on the stack. That's how it keeps track of how many times quadrant 4 got called. So if there are no more calls to quadrant 4 on the stack, it's time to return to the original call to quadrant 4. So we'll return to here. There's no calls left on the stack. It's the stack with no calls to quadrant 4 that tells the program that the recursion is done. Are you seeing the tie between recursion and loops? Often recursion is an alternative to doing a loop. What is a loop? It's the repeated execution of a block of code. Well, what are you doing when you do recursion? You're repeatedly executing the same code, the code inside the method. There you have it. That's recursion in the stack. Let's do another slide and get into a little bit more detail on how it works. I'm going to call this the recursion after example. We're going to add a print statement to the recursion, and we're going to add that print statement after the recursion so we can kind of see when the code executes. The previous examples, it was really kind of hard to see what code was executing when. So by putting a print statement in, we'll see how it actually works. You can see my little example there. Call me is going to execute call me in the middle and do the recursion. Let's move on and trace some code. So here we have it. A method called SearchMe. It takes a parameter int count, and it is a recursive method. In the middle of SearchMe, we're going to execute or call the method SearchMe. So call the method SearchMe, passing it an argument or value of 2. So we're going to start off with executing this line of code, SearchMe, and passing it an argument or parameter of 2. Also, I'm going to keep track of which calls are now. See this //:1? Think of that the address, or which call to SearchMe executes. We've called SearchMe, so we're up here to execute the first line of code. What happens when we execute the first line of a recursive method? It gets pushed onto the stack. So the :1 here is to say it's this call to SearchMe that called SearchMe. The parameter or argument is 2. So you can see count is set to 2 on the stack. So the call to search me is pushed on the stack, and the parameter count value equal to 2 is on the top of the stack. The currently executing method is always on top of the stack. So we'll go into the code here, and we'll ask if count is greater than 0. That's 2 greater than 0. Now I'm not going to draw it as a separate variable this time. Where this value is getting stored is on the stack. You can see count is 2 right here. That's where this 2 comes from. So count is 2, 2 greater than 0 is a true, means we're going to execute the code in the if statement. And what does that mean? Whoop, recursion. We're going to recursively call ourselves, passing it count minus 1 as the parameter. Well, everybody knows 2 minus 1 is 1. So 1 is going to be the new argument past the variable count. Now when we execute SearchMe again, the recursive version of SearchMe, you can see that SearchMe 2:2 was put on the stack because this call to SearchMe is the one being executed now. And you can see the new parameter value, our argument is 1, and that's stored on the stack as well. Call to SearchMe and the count equal to 1 is now on the stack. The top of the stack is always the current or active execution of the method. So we test our if statement again. 1 less than 0 is true. Again, count is over here. See, count is from this top of the stack. 1 greater than 0 is true. So we're going to execute the code in the if block, which means, whoop, more recursion. So there we are. We're going to recursively call SearchMe. The value passed to count is going to be 1 minus 1 or 0. Remember, the top of the stack always contains the current value of count. So we're back executing SearchMe. This is the third execution of the method SearchMe. Again, the :2 says this is the call to SearchMe that executed. And the value of count is stored there on the stack at the top. Count is currently 0. Remember, the top of the stack is always the current executing method. Which is interesting because 0 greater than 0 is now a false statement. See that 0? We're testing count 0 greater than 0. That is a false statement. We all know what that means. We've got to skip the if block and go right past it to execute the line after the if statement. And the line after the if statement is a system print statement. So when count is 0 per the top of the stack, the recursion is done. It's finished. It's no more. It's complete. We want to execute the code after, in quotes, the if statements. That's why this is called the recursion after example. The print statement is after the recursion. So when we fall through to there at that point and finally execute that print statement, we'll print count is, and we'll get the current value of count off the stack, which is 0, and you can see that's what gets printed out. Do you see it now? You can kind of see what's happening here. When the variable with count was 0, we fell through and executed that print statement, which means we hit the end of the method SearchMe. When we hit the end of the method SearchMe, what happens? First of all, I want to point out that we popped off something from the stack. We took the executing version of SearchMe where count was equal to 0 and it went gone. It's gone. It's gone. Now I left something a little bit here in red to remind you of who did call that version of SearchMe, because we need to return to that version of SearchMe. SearchMe :2 was called. So this call, when count was equal to 0, is the one that just finished. So we popped it off the stack, and we've got to come back and execute the line of code after that call to SearchMe. The call to SearchMe where the parameter was 0. So when we come back, we're going to jump to this line of code and execute it again. Use that address off the stack to tell you where to go back to. So we're coming back to this line. Remember, there was a call to SearchMe where the count had the variable or value of 1. We've got to go back and finish that call to SearchMe. So count is equal to 1. So when print count is executes, we'll take that 1 off the stack and we'll print it out onto the screen. There you go. Count equals to 1. Bang. We hit the end of the method SearchMe. When we hit the end of the method SearchMe, we got to go back and finish other calls. You can see we popped off the stack because SearchMe finished where count was equal to 1. So the call to SearchMe1 is done. Pop it from the stack and use the popped return address. Remember, it was telling you SearchMe://2 was called. So we got to go back after this call finishes and follow the line below it, which is this print statement right there. At this point, we'll output the print statement once more. Count is, you can see the current value at the top of the stack is a 2. So the 2 is what shows up on the screen. So why did we return to this print statement? Remember, the previous stack pop said SearchMe://:2 was the one that executed. And we need to execute the line after that line of code. Well, what's the line on a code after this one? It's that print statement right there. And the variable count is as the value of 2. So that's why the 2 showed up. Now we have to exit SearchMe for the call with a count equal to 2. We pop that off the stack. But remember, I left that little sort of shadow there on the stack to say, oh, the line of code that called SearchMe is the one with the :1 on the end. It was this one. So the call to SearchMe2, or the original call to SearchMe, is done. We pop it from the stack and we use the popped return address, the //:1, and it's going to go back to this call to SearchMe. And when it comes back to this call to SearchMe, the line after that is this print statement right here. So we'll then execute that print statement. You can see the SearchMe is done. It's come out. There's no more calls to SearchMe on the stack. It means the recursion is over, and return to the line of code after the original call, which is that print statement SearchMe done. Pretty slick, huh? Notice the order of the output. The original value of count, the 2, was printed last because the print statement is after the recursion. This system.out print line here does not execute until that if statement goes false. Since it's a 0 that made that if statement go false, the 0 is what gets printed first here. You can see how recursion works a little bit. All we're doing is repeatedly executing the SearchMe method until a certain condition is met. Once that certain condition is met, we kind of unwind the calls to SearchMe. So that was the recursion after example. Let's do a recursion before example. Let's put the print statements, or add a print statement before the recursion, so we can again see when the code executes. Once again, we're doing recursion. That's where the method callMeMaybe calls the method callMeMaybe in the middle of the execution. That is a recursive method. Here we have it. Again, a stack is going to be very, very important for keeping track of what's happening and how many times findIt gets called. We're going to call a method named findIt, passing it the argument, our value of 1. You can see it clearly here on this line right there. We're going to pass findIt an argument of 1. So this is going to cause the code to jump up and execute the method findIt over here. So we jump to that line and execute it. The call to findIt and the parameter value slot equals 1 is pushed on top of the stack. There it is. The stack keeps track of how many times findIt gets called, where it's called from, and what is the value of its variables. Slot is 1 in this initial case. The print statement is right there at the beginning, so we're going to print out slot is 1, and the value of slot comes straight off the stack and gets printed out on the screen. Slot is 1. The print statement using the value of slot from the top of the stack outputs to the screen. Now we check the if statement. The variable slot and the value 1 are located on the top of the stack, and we are going to ask, is slot or 1 less than 3? That is definitely a true statement. As a true statement, it's going to execute the code in the if block. Whoop, there's our recursion. Method findIt is going to call findIt, textbook recursion. The recursive call to findIt, the value passed to findIt is a 1 plus 1, or a 2. Where are we getting that value of 1 from? From the top of the stack, of course. It's all about the top of the stack when a recursive method is executing. So the new value 2 is assigned to the parameter slot. The call to find it and the parameter value slot equals 2 is pushed to the top of the stack. This is now the currently executing version of find it. Our print statement is before the recursion, so it's going to print right away. The value of slot will come off the stack and be printed on the screen right here. Now we'll execute our if statement. Current value of slot is 2. You can see that on the top of the stack. 2 less than 3 is a true statement. We're going to go inside the if code and execute the code following the if statement. Whoop, there's our recursion. The current value of slot is 2, so 2 plus 1 is 3. So we're going to recursively call ourselves and send it the argument or the value 3 as the parameter. This is a new executing version of find it, so it'll be pushed onto the stack. You can see the value of slot has 3 now. So the call to find it and the parameter value slot equal 3 are pushed on top of the stack. Remember, the top of the stack defines the currently executing method. We'll print slot is. Slot has a value of 3, so it comes off the top of the stack and is printed to the output. But something interesting happens here. The current value of slot is 3, and 3 less than 3 is a false statement. So we will finally exit this if statement. This if will go false, which means we skip it and go to this closed curly brace. That's the last curly brace of the method find it. So we will be exiting the recursion. Now what happens when we exit find it for the call with slot equal to 3? Well, why return to this curly brace? You see that little arrow there? That basically says we're going to just turn around and come right back to where we were. Remember, when a call to find it finishes, we need to execute the code after find it. Well, that's that code right there. The previous stack pop said return to where there was a :2. All right, well, that's the call with the //:2 at the end. We have to return to the line after that line of code, which would be that curly brace. The new value of slot is going to be 2. So we'll hit this curly brace, and now we're going to exit find it for the value of slot equal 2. But we're just going to zip around and call ourselves again. So why return to this curly brace? Previous stack pop said return to the :2 call to find it and execute the line after find it. Slot now is going to be restored to 1, and we're going to finish the execution of that method. Now, slot equal to 1, when we exit find it for the call with slot equal to 1, that was the original call. That's what was stored on the stack. That tells us how many times we have to do it. We have now finished all executions of the method find it. So we're going to return to the //:1 here and execute the line of code after that. You can see there's a system.out print there. The prints find it equal to done. That shows up on the screen saying my recursion is over. So no more calls to find it on the stack. It means the recursion is over, and return to the line of code after the original call. Notice the order of the output. The original value of slot is printed first because the print statement is before the recursion. So when we called it find it 1, slot is 1 is the first thing that came out. And the last thing was printed out, slot equals 3, is the last call to find it. Oh, what can you do with this recursion? Why does it exist? Why do we want to even know it? Let's look at recursive binary search, a divide and conquer game algorithm. Whenever we're dealing with a lot of data and we need to search that data, we want that search to happen fast. So we're going to go back to the binary search algorithm and look at it in a recursive manner. First of all, the stack is key to executing recursion. So let's look at what happens to the stack while that happens. Binary search is what I call a natural recursive problem because it solves the same problem on a smaller and smaller set of data. It does require a sorted date array, so that is a requirement. You can see our data here 10, 25, 30, 45, 50, 65, 70 is in order. That is a requirement of binary search. Look first at the header for the recursive binary search. Use parameters to divide data in half for each recursive call. So basically what I'm going to do is I'm going to call binary search to search the entire data. Then I'm going to call binary search on a smaller piece of data. Then maybe call it again on an even smaller piece of data. The parameters, according to the header of the method binary search, are going to be array. That is the data we are searching for. There's the array. The second parameter is going to be key. This is the value we're looking for. The left parameter is going to be the lower bound, or where do we start the search from. That's going to be 0 in this case. The upper bound is going to be the right value. That's the upper bound. That's going to be the end of the data where we're going to search. So basically we're calling binary search and saying look for key between these two indexes, left and right. Now we're not going to look at the code for binary search. We're going to look at how binary search works. It's critical when you're learning to program, you understand how things work, not just memorize code. So we're going to call binary search and pass it 50 is the key, which simply says I want to find 50 amongst the data of my array. So your search is of 50, finds 50 among this data. Now the way binary search does is it's going to search between 0 and 6, our original parameter, search between 0 and 6. Here's the lower bound over here, bang. There's the upper bound, 6 over here. Now the middle of that data is going to be slot 3. So the middle value that we're going to start our search at is going to be right there at position 3. Remember, binary search says go to the middle of the data and decide whether to search left or right. Now look what got pushed onto the stack over here. The parameters and our variables got pushed into it. Binary search was called. The key was 50. That's what we're looking for. The lower bound or left was set to 0. The right bound or the upper bound is set to 6. That's why we got a 6 here. And then we calculated the middle, and the middle was calculated to be 3. We're storing all that information on the stack. 50 is less than 45. The value we're looking for, 50, is less than that value right there. So what does that tell you? That 50 must be on the right. We need to search this half of the data and ignore the other half of the data. Since what we're looking for is bigger than the middle item, we need to go to the right. Now, what are we going to do? We're going to recursively call ourselves to solve the right hand. So we're going to recursively call binary search, and we're going to change left to search the upper half. See this blue arrow here? That was over here, but our comparison said we had to be to the right, so all I did is move that blue arrow from here to there. So you can see on this call to binary search, the key is still 50. That hasn't changed. But the left bound, the lower bound, has moved up to 4 because what we're looking for is greater than 45. The right bound stays exactly where it was at the end of the array. And somewhere between 4 and 6, we should find our data. The middle is then calculated again, and the middle of between 4 and 6 is 5. 4 plus 6 is 10, divided by 2 is 5. The middle of our search range is 5. So that's what binary search says. Now search this data right there. How are we going to search that data? Well, 50 less than 65 is a true statement. What we're looking for is less than 65. So binary search says we have to go to the left and look for that data. Bang! When we go left, we recursively call binary search again. Still looking for 50, but this time left will be 4, which it was at before. Right has moved down. See that green arrow? That green arrow used to be pointing here, but when we looked at 65, it said we have to go left, so the green arrow moved to here. Now basically everybody's pointing to 4 right now. Left is 4, right is 4, and the middle is 4. What's going to happen now? This is different. We go to the middle and test it against what we're looking for, and 50 does match 50. Well, we have to be happy now. We were searching for 50 and we found the position of 50. It's at index 4. We need to return the 4 to whoever called binary search to let them know we found 50 at position 4. So we're going to execute this slot equals after binary search is done, and whatever value here in middle 4 gets transferred to the variable slot. So 50 was found at position 4. That's what we expect to be assigned to the variable slot. Now I kind of got rid of a lot of stuff off the stack. Binary search doesn't have to do any more comparisons once it's found its target, so it does a return and all the stuff gets taken off the stack. New binary search. Let's use the array.length property instead of a hard-coded value. This code assumes that all the array slots are used. We generally prefer not using hard-coded values. I know I do a lot of them because we need to keep the example short. 50, 0, and 6, these might be coming from variables, not hard-coded. 30 and 0, 30 is what we're looking for, 0 is where we start. This time, instead of a hard-coded 6, I've got to do array.length minus 1. Remember, the length property tells you there are 7 items in this array. If there are 7 items in this array, length minus 1 or 6 should be the last item in the array. This code is assuming you're going all the way through the entire array to the end. So let's do our search again, this time for 30. Execute the call to binary search and pass it 30 as the parameter. Compare 30 to the middle item, right? And locate 30 in the sorted array. Binary search is now executing. Binary search is executing between 0 and 6. The lower bound or left is 0, that's the blue arrow. The upper bound or the right is 6, length minus 1 is 6. So search between 0 and 6. First thing we do is calculate the middle, and the middle calculates as 3. So you can see pushed onto the stack, we're searching for 30 between 0 and 6, and the middle of the range is a 3. So let's start at the 45 and begin our search for 30. 30 less than 45 is clearly true, so 30 must be to the left. If this is a sorted array, then any numbers smaller than 45 have to be on this side of the array. Let's recursively call binary search and adjust our search parameters. Recursively call binary search, change right to search the lower half. Remember, right is this green arrow. It's moved from here all the way down to here. If what we're looking for is less than 45, we want the right side of our search parameter to be right there. So you can see we're still looking for the value 30. Left is still 0. Right now has changed all the way down to 2. And when we calculate the middle, 0 plus 2 divided by 2 is a 1. The middle of this search range is subscript 1. So how do we search this smaller range? Recursion, of course. 30 less than 25 is false, so we need to go to the right. How are we going to go to the right? Recursion. Where recursively call binary search, we'll change the left parameter this time to search the upper half. So that blue arrow went off as 0 and moved it up here to 2. You can see on the stack, key is still 30. That's our target, what we're looking for. Left is 2, right is 2. We keep adjusting these parameters depending on which direction we want to go. And now the middle calculates to 2. 2 plus 2 divided by 2 is a 2. This is this is a terminating condition. It turns out we've found our 30. When we go to the middle item of our range and ask is 30 match 30, it is a true statement. We found it index 2. We need to send back the 30 is located at position 2 of the array. So this slot equals here has got to get to 2. You don't send back the 30, you send back 30 was at position 2. And you can see the 2 from the middle variable is sent back and is going to be assigned to the variable slot. 30 was found in position 2. And of course, once it returns that, whoop, the stack can go away. We don't need anything else on the stack. There's no code below the return statement in binary search. Binary search typically returns a negative number when a search fails. It's hard to see on a small array, But the speed improvement is huge when you talk about a binary search of a large array. Let's say you were searching a million numbers. The first number you compared, that middle item, chops your data set down to 500,000. By comparing one number, you eliminated 500,000 different possibilities. Then you go to the middle of that range and you can do a second comparison. That second comparison chops your search area down to 250,000 items. So every time you compare one number, you're throwing away half the remaining numbers. Turns out you can search a million numbers by just looking at 20 of them. Turns out 2 to the 20th power is about a million. It turns out mathematically you can chop the number 1 million in half 20 times. After looking at 20 values and 20 only, you can binary search an array of a million numbers. So we definitely want to use that binary search algorithm. It's much faster than a linear search. When doing searches in a large video game, you want to make sure there's some sort of binary searches. I'm going to wrap it up with this last slide on what's called Quadtree collision detection, another divide and conquer game algorithm. Quadtree is another natural recursive problem because it solves collision detection by dividing the problem into quarters, then calling itself to solve for the correct quarter. It's twice as good as binary search, which only divides in half. Basically, we're talking about the same concept. Divide my search area into 4 parts instead of 2 parts like binary search does. Clearly a divide and conquer algorithm. We're going to divide into 4s or quarters. So here's the problem. We want to determine if and where Mr. Happy Face collides with any star on the video game screen. Here is our screen. Think of those stars as objects, right? We're going to have objects that we can run into on the screen. And as Mr. Happy Face moves around, we want to know when he bumps into one of these star objects. Wrong way to do this is to compare Happy to each and every star and see if they overlap. Compare Happy Face to this star and this star and this star and this. That is the wrong way to do it. We don't want to compare Happy Face to everything else on the screen. That's just going to take way too much time. So the right way to figure out collisions, who does Mr. Happy Face collide with, is to use Quadtree. Quadtree says divide the screen into smaller and smaller quarters and only check the correct quarter. So let's see what we mean by that. Boom, I've overlaid these green lines on the screen to kind of divide my screen into quarters. I've divided the screen into 4 quadrants. Clearly Happy only resides in one of those quadrants. What does that mean? It means I only have to check the star objects in that quadrant for collisions. I'm going to ignore the other 3 quadrants and recursively call Quadtree for the correct quadrant. I don't have to search here. I don't have to search here. I don't have to compare here. None of these need to be compared because Happy Face is in this quadrant. Recursively call ourselves for that quadrant. Now, that is a lot of star objects that do not need to be checked, but there's still many in the current quadrant. What to do? What to do? Well, if it worked once, let's recursively do it again. Let's call Quadtree recursively and say, divide this area into quadrants. So divide the smaller section into 4 smaller quadrants. Clearly, Happy only resides in one of these subquadrants. What does that mean? It means we only have to check the star objects in that subquadrant for collisions. Ignore the other 3 quadrants. I don't have to check here or here or here. That's 6 more checks I've eliminated from my test to see if Happy Face has collided. Let's recursively call Quadtree on the correct quarter, this quarter only. Bang! More star objects that do not need to be checked. At this point, there are so few star objects in our quadrant, time to check for collisions. And it, in fact, finds those 2 stars collide. There's a collision right there. There's a collision right there. Now, how many times it divides in quarters depends on how many screen objects there are. The more objects you have, the more dividing you do. If I was trying to check 1,000 different objects, I'd have to sub-quadrant many different times. I'd recursively call myself more. The total number of objects you want to see if you collide with determines how many times you recursively call the Quadtree algorithm. Note, I restored the stars. I put the star objects back. They didn't actually go away. They were just hidden to show that I don't have to check that. I don't have to see if Happy Face ran into a star that is in a different quadrant. In a complicated game with 1,000 possible collisions on the screen, Quadtree can greatly improve performance. Instead of checking 1,000 different objects to see if you collide, maybe you can get it down to 5 or 6. Repeatedly divide the screen into quarters and only check the quarters for collisions. So let's move Mr. Happy Face and do it again. So as Mr. Happy Face moves across the screen, he enters a different quadrant. The Quadtree selects a different quadrant and recursively calls itself on the new quarter. Bang, I don't have to check any stars in that quadrant. Since this quadrant has so many star objects, again, I'll recursively call Quadtree again and divide that section into quarters. See the recursion? I'm going to drill down, selecting the proper quadrant until what? Until we reach a reasonable number of objects to check. At this point, there are so few star objects in this quadrant. Stop trying to divide and conquer by checking for collisions of star objects in the quarter. And in this particular case, no collisions were found. The only 2 star objects in the same quadrant had to be checked, but they did not collide. So rather than check all of these star objects, I only had to check the 2 that were closest to Mr. Happy Face. Note again, the star objects did not actually go away. They were just hidden while I showed you how the algorithm works and showed you that you do not need to check for collisions for objects that are outside your quadrant. In a complicated game with 1,000 possible collisions on a screen, Quadtree can greatly improve performance. It's the difference between a sluggish game and a fast game. I must admit, it's an overly simplified explanation of Quadtree algorithm. You're going to need a data structure course to learn how to build the tree properly. See in the data structures class, maybe? Hopefully so. So there you have it. That's recursion. Recursion is used a lot in game design. It's important to understand how it works with the stack and how it reduces a problem from a big problem to a smaller, to a smaller, to smaller. Good recursion means every recursive call should reduce the size of the problem. Binary search chops it in half. Quadtree chops it into quarters. To wrap it up, recursion is simply a method that calls itself.